Auto level requirement for Brain2 or IKON flybarless system. To electronically set up the auto level feature of the Brain2 or IKON flybarless control system is very easy. It's just one tick button and you are done. But this does not mean that the helicopter will hover without drifting. If the CG of the helicopter is not at the center of the main mast, the helicopter will drift on hover. If you have excessive vibration, it will also drift. To overcome this, the CG has to be adjusted and the vibrations has to be minimized. First, the requirement of the Brain2 or IKON flybarless system is to disable the trim buttons of the radio. If your radio does not have a function to disable the buttons, you must set the trims to 0 and never move the buttons to correct drifting issues of the helicopter. Drifting issue must be corrected by another way when using the Brain2 or IKON flybarless system. Why? Because during initialization the value of the transmitter's aileron, elevator and tail potentiometers is read at every power-up and uses the new center, 0, value during operation. So, any trim you apply from a previous flight will be reset to 0 the next time you power up the helicopter. Using a swash plate leveler, adjust SRV1, SRV2 and SRV3 accordingly to level the swash plate. Follow the instructions on this slide. I used a digital pitch gauge to level the helicopter by suspending the helicopter at the main shaft. I used a bubble level to set the pitch gauge to 0. I suspend the helicopter at the stabilizer bar. This way, the helicopter is free to tilt along the X and Y axis. If the CG is perfectly at the center of the main mast, then the X and Y axis must be level. Using the digital pitch gauge, I position it along the X and Y axis and adjusted the battery until the reading of the pitch gauge is 0. Then I put the helicopter on top of a table making sure that the table is level. Activate throttle hold and put the throttle stick somewhere at the middle until the reading of the pitch gauge is 0. Rotate the blades along the 4-axis and adjust the swash plate in the FBL unit, tab 8, to get 0 reading on the first, second, third, and fourth quadrant. Do not use the trim buttons or sub-trim function of the radio. If the pitch is not 0 on a quadrant, the helicopter will drift on that quadrant at hover. Some people will use a swash plate leveler, which is a good starting point, but the final indicator is the blade pitch along the 360-degree path of the blade are the same. There are linkages from the swash plate to the blade grip that may be a source of imperfections. Only the pitch gauge can confirm this. Before starting a vibration analysis, I installed a mounting gel at the bottom to the flybarless unit. But I am concerned that it might come out during flight. Some people put a small gel sheet at the corners of the FBL unit and tie it with a cable tie. But I decided to DIY a mounting assembly wherein I can put a small mounting gel on top as shown, but only one side is sticked at the top cover. I did not remove the cover of the mounting gel touching the FBL unit so that the FBL unit can freely move. The technique I used to analyze the source of vibration is divide and conquer. First, I removed the upper frame of the helicopter including the clutch and bell assembly, leaving only the motor into the equation. Then I let the motor spin and measured if there is excessive vibration coming from the motor. You may need to send the motor for balancing if you spot excessive vibration in this step. But you are very unfortunate if this will happen. This is the vibration data on normal mode. The global vibration recorded is 4. This is the vibration data on idle up 1. The global vibration recorded is 2. This is the vibration data on idle up 2. The global vibration recorded is 2. Only a very negligible vibration was observed. I installed the clutch and bell assembly and repeated the same analysis. The vibration data on normal mode is 6. The vibration data on idle up 1 is 12. The vibration data on idle up 2 is 13. Vibration has increased a little bit, but it is still within the allowable level. Then I installed the main mast assembly, but without the rotor head, and repeated the same exercise. The vibration data on normal mode is 7. The vibration data on idle up 1 is 11. The vibration data on idle up 2 is 7. Vibrations is still within the allowable level. Then I installed the rotor head without the blades and repeated the same exercise. The vibration data on normal mode is 26. The vibration data on idle up 1 is 48. The vibration data on idle up 2 is 81. Vibrations is still within the allowable level. Lastly, I installed the main blade and repeated the same exercise. The purpose of this step is to locate the master blade that will give us less vibration. I have marked one blade with master and stick a sticker at one of the blade grips. The vibration data when the master blade is installed in the blade grip with a marker is 92. Then I reverse the blades. The vibration data this time has increased to 122. Which means vibrations is lowest when the blade marked with master is installed on the blade grip with a marker. From here on, this will be the positioning of the two blades. So far up to this point, I did not find too much vibration. It's now time to test a helicopter in the field. Hovering with the auto level off is perfect. But hovering with the auto level on has a small forward and to the right drift. Which means this FLB unit does not like any vibrations at all in order for the auto level not to drift. Impossible to attain on a helicopter. I tried adjusting the phasing of the main blades, but it did not help.